Hi CPC folks, here's another update from the Blue Pill-based CPC expansion card project. I'm going to create a Blue Pill microcontroller based extension card for the CPC. In my last video I showed you that little basic program that you see on the screen here. And I already have some version of a firmware running on the Blue Pill, which is a simple port echo program. So any I/O request byte it receives at port FBEE, it stores like a flip-flop, and the next read request that comes to that address is echoing that byte back. So it's basically a port echo program, right? And I showed you this basic program, which basically computes a random byte, line 10, right? It outputs that random byte to port FBEE using the out I/O write request, and then it reads back from the same port into variable B, and we are expecting that A and B are identical because this is what that little echo test program on the Blue Pill is doing. And if there is a mismatch between A and B, we print an exclamation mark, and I showed you this, and I'm going to show you that again, that we are now creating a lot of I/O requests to that port, and we are not getting any exclamation marks, so that's a good indication that that port protocol from the CPC to the microcontroller is working well. And I also showed you if I pull a bit here, right, then exclamation marks start showing up because of course a bit is now missing from the byte that we are reading back. Now you can say, okay, so this was just the plain CPC 464 with no expansions connected to the bus. And also it's a basic program, so it's running slow, right? So you rather want to make sure that your hardware extension that you are designing also works in combination with other expansions connected to the bus, and of course also with higher I/O throughput rates. So to this end, I have now connected the DDI3 floppy disk emulator to my CPC 464, and I also have a ROM board here. And you see that the ROM board actually contains the ROM of the MAXAM assembler, which we are going to use. So let me this time load a test program from disk. First I'm going to select the disk here. And this is basically the same echo byte test program that I just showed you in BASIC, but this time written in MAXAM assembler. And rather than creating a random byte, it's just counting from 0 to 255 and in a loop, right? So the great thing about MAXAM is you can use the basic IDE, so to speak, right? The basic editor, and it integrates with Locomotive Basic very well. So you can write assembler in BASIC, which is great. I love that experience, you know, it's like in the old days. Of course, I could also program assembler on this PC using one of the modern emulators. Many of those have the AD assemblers built in, right, which are of course more productive, but I just like and love this old retro authentic experience. It's just like programming assembler in the 80s, and that's for me one of the main reasons to actually tinker around with these old machines, because I love that old retro authentic experience. So you see we have the counter bytes there, right, in line 190, and so here's a little routine that outputs a text basically. Press a key, and after you press the key the program starts. So it starts at next here. First we are loading the current value of the counter into the accumulator. That gets output using call out a subroutine to the port. Then we are reading back the from that same port the echo byte that was sent by the Blue Pill to the CPC, and we are comparing the two values. So I'm storing the return value from the call in a subroutine in register B, and I'm comparing B to the counter. If they are identical, then it's good. If not, then we are jumping to the label bad, and the label bad is outputting something on the screen, a single text character using the firmware write text character routine BB5D. So that puts the character which is bad, basically the counter value, on the screen. And if not, everything was good, then we increment the counter and we loop basically, right? So we're running in a loop here. And now this with additional extensions connected to the bus and the maximum I/O throughput possible, right? Because it's running in assembler now in machine code. And of course, out A and in A, the subroutines, they do what you would expect. So they load the port address into the BC register pair, FBEE, and then out and in opcodes of the Z80 are being used to either output the accumulator value to that port I/O address or to read from that port I/O address using the in Z80 command, right? So let's compile that and see if that also does, right? So press any key to start. I'm doing that now, and so if everything, I press the key now, it's running. So if everything goes well, then we don't expect any output because A and B always match, right? And which is the case here. Again, if I'm pulling a bit here, like I showed you earlier, right, then it's producing output on the screen, and it only advances the counter after a successful write-read pair. So this explains why the counter is stuck. You know, if I pull a bit, then it continues to be bad, then it doesn't advance the counter. And you can say, okay, that looks slow, but actually it isn't, because most of the time is being consumed by the printing routine for the screen called NBB5D, text out character, right? So it's doing hundreds, if not thousands, of I/O requests to the BluePill now per second, and it's working reliably, right? So that's a good indicator that our protocol and our interface to the BluePill is really working well and without flaws. So, but I actually wanted to show you something more interesting this time. I mean, this is of course only a test. I'm going to use this as a basis for an extension card, right? And the idea of that extension card is of course that I will only have a carrier PCB. Into that carrier PCB I'll just plug in a standard $10 BluePill that you can buy on eBay or Amazon for $10. So I don't need to solder that much, right? And then the only other thing I really need on that PCB is that little GAL address decoder chip here, right? Which you can see here, but there's no other circuitry or logic required. Everything else is done in software by the BluePill microcontroller, right? So there's no transistor or capacitor involved for holding down the ready signal of the CPC, right? So that's all done in software by the BluePill because it's fast enough. And the ISR handlers, the interrupt service request handlers that are processing the I/O read and I/O write requests, are basically triggered fast enough with a 72 megahertz clock of the BluePill, right? So this is why this is possible. So, but this time I actually extended that program a little bit. So rather than just echoing back, you know, the byte it receives to the port, it also sends it to one of the UARTs, and I have connected an FTDI cable to my Ubuntu EPC netbook here, right, which is still working flawlessly. And you can see the FTDI cable here. This is one of the fancy ones, which even has LEDs for RX and TX, so it's blinking like crazy because it's receiving bytes. And here the FTDI cable loops around and comes back here, and you see how it's connected to the BluePill here, right? So we have, that is the ground wire, and then we have two other wires here for TX and RX, and those connect to the 5 volt, one of the 5 volt compatible UARTs. So so the MINICOM program here is of course now showing the counter bytes from 0 to 255. A more useful test case is of course something like a terminal program, so that sends basically text from the CPC to the Ubuntu PC, and I also wrote that in BASIC here. So let me just run this BluePill serial and it's giving me a prompt: BluePill sent to PC. Hello, this is the test, and you can see that it's correctly showing up in the MINICOM on the Ubuntu EPC, right? Okay, so this is where we are now. We still have one UART left on the BluePill, the 3-volt compatible one, and basically I'm only going to use the transmit the TX 3-volt pin in order to control some other UART extensions basically with that interface. So if you watch my next video, which is going to be released soon, then you will know what I'm going to do with that additional UART. Alright folks, that's it for now. Thanks for watching. Bye.